How you doing? I'm Mr. Rose, and today we're going to go over a couple of examples. Well, actually, just start with one example per video. Here we're going to do a simple example of just an RC circuit, as you can see. First thing I'm going to do is I'm going to draw the circuit. So I'm going to draw a capacitor here, add a switch to it. Going to put in my resistor. And now I'm going to define sides of my capacitor as just positive and negative. And now what that's going to do for us, obviously, let me actually add some other things. I know V naught, the initial is 100 volts. I don't really need to put that near my, my picture if I don't want to. But what this does in my definition here is this is going to make it so I can define the direction of my current. Right? So I'm going to define the current I know traveling in this direction. Guess I can put a little current flow in that direction. So if I wanted to now, I can add little current arrows just traveling around. And that's important so I can apply, obviously, hopefully, I want to show that I'm going to apply the loop law here in order to solve what we're finding. Now, initially, we're going to find our time constant. And remember, when we're solving RC circuits, it seems like we take a roundabout way because there's so much going on. So the first thing, looking around for my calculator now, first thing that we want to do is apply that loop law so we can figure out, voltages and currents going around our circuit. So I know if I'm starting, I should have the potential difference minus now IR here, get back down, equals 0. Just following that along. And what we should start to remember here is we should know that V is going to tell us something. We know V with regard to my capacitor, right? We know V is equal to the charge of my capacitor divided by the capacitance. So I'm going to sub that directly in. And now I can say that is my initial charge of my capacitor divided by my capacitance minus IR equals 0. Now again, we're thinking, where is this time constant coming from? And we have derived this equation before, where I know charge, like here's my initial value, my charge through my capacitor, at my capacitor to start. But I know the charge Q and my current I know those guys are going to vary with time. Those are variables. So I'm going to actually try and find common variables between my Q and my I. And I should know that I, by definition, is just a charge per unit time, which means I can also say it's a small charge per small time. So now again, I get to redefine some more. I can say that my initial value minus my R, dq over dt, that whole thing times my resistance is equal to 0. All right, so now I have some common terms, which is a little good. But again, we have to know some stuff about physics. This is why physics is not just straight memorization. We need to know that I is by definition charge per unit time, and that is going to yield a positive value in its original form. So I need to cheat a little bit. I need to say, based on my discharging the capacitor, because again, this is a discharging capacitor, I need to say that my dq dt has to yield some negative value, right? So I need to actually know that this is saying minus this negative dq dt. So in reality, I need to know that my capacitor is discharging, so it is losing charge per unit time times the resistance is equal to 0. So this is going to be helpful such that we can continue. I got to move up a little bit here. This is going to be helpful so we end up with the right values. Remember, charging and discharging capacitors are very different. So now I have my charge equal to, that's going to be plus a positive, it's going to be equal to negative dq dt times r. So now I'm going to start to rearrange. Let's see, I want to get my r by itself. So now I'm going to have my charge, not my r by itself, my charge per unit time, my varying charge here, or my current, divided by r times the capacitor, is negative dq dt. And now if we recall, this RC, that's what we're looking for, our time constant. So we can redefine tau if we want as RC as just a reminder that this is what we're solving for in the time constant. So here I have, what do we got? Negative dq. Oh, I don't like that. I want to get those variables together. So I'm going to do one more thing here. I'm going to say rearrange here, multiply and divide. dt over rc equals, now I've got a negative dq over the initial charge of my capacitor. So now I have my variables all together, and now I can integrate, since this is my time constant with respect to time, and I have a charge and a charge, I get to integrate both sides. We know that at my starting point, at time t equals 0, I know that what I'm calling my charge of my capacitor, that was just my initial charge, right? So now to get my time constant to itself, this is something we've done before, I take the integral of both sides. I'm going from 0 to t over here. I'm going to integrate on this side from my initial value, q naught, to my varying q. I know q changes with time. Find some more room here. So I know, I know q changes with time, and now I have just some straightforward antiderivatives or integration, where when I take the integral of dt over rc from 0 to t, that should be easy. I'm just going to get negative t over my constant rc. And that's going to be equal. Now here we should recognize a natural log, right? I'm going to take the antiderivative of dq with respect to q. That's going to be the natural log of the absolute value, because I'm going from q naught to q, the absolute value of q minus the natural log of q naught, which I'm going to say is my initial q. And I can rearrange this again, just some identities, over RC equals the natural log of Q divided by Q naught. So this is going to be a straight kind of practice problem here where we need to remember how to integrate these. If we don't remember this, now I'm still not done here. I mean, I want to solve for this time constant, and I can make this easier. I know I need an absolute value sign there. I know to get rid of my natural log, I need to raise something to a power of e. So I know that in order to find something with respect to q, now granted, I'm not looking for q. We're looking for the time constant, which is r times c. But I know that q varies because of the time constant. So essentially, I want to get some expression with q, whatever my charge is, at some time later. And this yields, solving for q, getting rid of my natural log, we can remember, well, we can either commit it to memory or be able to prove this, that q is equal to q naught e to the negative t over rc, where this q naught is what I have as a capital Q naught here. That is my initial charge of the capacitor. This is my time varying charge. This is my time constant RC, and this Q is for any time t. Now, what we were trying to solve initially with this problem was, what is my time constant, part A? What is my time constant for the circuit? So I am essentially searching for that RC, my tau. And that's what I have here. Now with my initial conditions, let's see. So I'm trying to figure out how this is going to be helpful to us, like I said, with our initial conditions. And what we stated to get here is going to be another little trick. To go back, I know V is equal to Q over C. Well, I've got this nice expression in terms of charge. If I only had an expression in terms of a potential, because I was given an initial potential. So if I divided both sides by the capacitance, if I said Q divided by C is equal to Q naught divided by C times e to the negative t over RC, there's my time constant. What did I do? Here, I redefined for some potential at some later time. Here, I defined my initial potential difference. And now everything else stays the same, where I have an e to the negative t divided by RC, my time constant. All right, well, now I can make a ratio, divide both sides. V divided by V naught is equal to e to the negative t over RC. Now to get rid of that e, we're going to do exactly what we did before. I'm going to take the natural log. I can say the natural log of V over V naught is equal, that gets rid of that. Now I have a negative t divided by RC, where that RC is my time constant. So all I now need to do is rearrange. I can say, oh, I'm sorry, I didn't realize I was off the script. There we go. As I said, we're just dividing through. Now, finally, I can find for my time constant, my tau or my RC is equal to negative t divided by the natural log absolute value of V minus V naught. And now with my initial conditions, sorry, couldn't find my natural log. There's just this. I should get some Jeopardy music going on. The natural log of over, we should get tau equal to, oh, I just made a mistake, 2.17. Whew. RC, oh, wrong paper. RC is equal to 2.17 seconds. Now the mistake that I made is in my initial conditions, my initial mistake, I used t equals 17, I looked at part B. We know that at time equals 10 seconds, my voltage V drops from 100 to 1. So this should, if we get this far, just straight plug and chug, 10 divided by the natural log of 1 over 100. Make sure that's a negative. So then for part B, find V at 17 seconds. This is easy. This should just be straight plug and chug of what we have, right? I know V equals V naught e to the negative t over, I'm going to just rewrite it as tau, even though I have RC. Remember, tau and RC are the same thing. So literally it's just that V is equal to 100 times e to the negative 17 over 2.17. 100. E to the negative 17 over 2.17. 0.0, so V is equal to 0.0396 0.04 volts. So this was a very straightforward, let's apply a loop law. Ooh, I'm upside down. I'm going to leave that in there. This is a very straightforward, let's apply a loop law and find a time constant and a potential difference as my capacitor discharges. That is, I'm going to try over here. Now I can't see the screen, so I might be in. That's all I have for you on this example. I hope you followed it. Please, hopefully you tried this before you saw it. Please feel free to like, click, or subscribe. And I'll see you next time for another example.